it to be high, and on every clock edge we gave a new data sample. And what we did ultimately we calculated the frame energy. This is the energy, this is the data sample. And we know that clock is working at 100 megahertz and the time duration of the clock is 10 nanoseconds. So for every 10 nanoseconds, we have to give one sample of a signal. So once we set the frame size to be 8, for every 8 samples, we have a data value to be high. The module has taken all the 8 samples and it has calculated the energy value. So how to give all these samples? We have to give at this clock rate, 100 megahertz clock rate. Or else, even if you are giving it a 50 megahertz clock rate, then what you have to do for whenever a sample is valid, at that time what you have to do, you have to make a sample valid. So you have to give these pulses. Instead of a single pulse, since we gave each sample in each clock cycle, we gave a single pulse. Uh, not a single pulse. We have a single low to high and high to low transition. So if you are giving at unique clock cycles, then what you have to do? Then you have to give a pulse signal. When this pulse is active, then it indicates that the sample which is coming on this data line is on the frame sample is valid. So we need to find some mechanism through which we can send the data samples to our module. So we cannot do it manually by hand or by the slide switches. So we have to give it in the order of 10 nanoseconds. Maybe if you are giving each sample it in each and every clock cycle. So for that, what we have to do, you have to design your own controller and another module. That module, I'm calling it as data source. So the main idea is we have a data source module like this, and then we have our frame energy module like this. So what we do is we trigger this data source. When we trigger this data source, what it will do, it will trigger the frame energy module, and then what it will do, it will give the required data to the frame energy module FE. And whenever it is giving it the data, it will also tell when the data is valid. That means it also gives the data valid signal. And then the frame energy takes the data from the data source, and then it calculates the frame energy and it will give you the energy value. And whenever this energy value is valid, a valid signal will be given. So in this mechanism, we have to do it if you want to implement on an FPGA. So this entire block, what I am drawing, this entire block should go on an FPGA. Then only you can able to visualize how the energy is being computed in real time on the FPGA for a signal having a finite length samples. So anyhow, the frame energy module we have designed and it is ready. Only thing is, if you make the availability of this data source, then we can integrate these two things, and then what we can do, we can connect this data source to with the frame energy. And what we can do is this frame energy output, that is energy, we can connect it to the integrated logic analyzer that we have seen in yesterday's class. And through this integrated logic analyzer, we can visualize. So energy value and a valid signal, we can connect it to ILA and we can visualize. And this data source can be controlled externally by using some start input that is connected to maybe VIO output. So in this way, if we can establish, then we can check this functionality in hardware. So what we can do now is, I will just explain you how to design this data source. We will see. Since we are running short of time, we will end for today with the design of the data source. And tomorrow what we'll do, We will quickly integrate with the frame energy module and we will check it and verify it on the board. So without wasting any further time, what I will do is I will just data source is a very simple block. What I will do is I will just explain you the Verilog code how to do it. So the data source, this is the top module of the data source. The main idea is inside it consists of a memory unit, and we also have a control unit. Okay, in this memory what we do is we directly take some data in a text file and store it in the memory, and then we will design a control unit where it establishes the two-way communication. Then what it will do is upon receiving an external trigger, that is start, the controller, what it has to do, it has to read the data from the memory and it has to output. While it is outputting, it also needs to acknowledge the valid signal. So data should come out and a valid signal also should come out, and this process should repeat until all the data samples are read continuously. Once all the data is read, then it has to go. It has to go to the idle state. And to this control input, the controller also needs to know what is the status of the frame energy block. So it has to initiate the data transfer to the frame energy. When frame energy is in the ideal state, then only it has to trigger. See, we are integrating this data source with the frame energy block, right? So this frame energy, we have used one output called ready. When ready is logic high, it indicates that frame energy is in idle state. That is, it is not doing any job. So this should be fed as an acknowledgement to this. And when a start trigger is being applied here, then the data source, what it needs to do, it has to scan this status of the frame energy. If this is ready, then only it has to trigger the frame energy. Then frame energy module will switch to the first state 1 from S0 to S1. Then what it has to do, it has to send the data and it has to acknowledge. Then what it has to do, it has to receive the data and compute the energy. So once all the memory samples from the memory are read out, then the data source should stop the data streaming, and frame energy will give you the output and it will switch to the ideal state. If at all, if any other trigger comes, again the frame energy is in ideal state, so again data source will trigger the frame energy module, then it will start initiating the data transfer. So this is how the concept looks like. So for this, how do we design a hardware circuit? So for that, I'm not doing it in Vivado. I will just do it in a notepad file, and tomorrow I will share you this file. Maybe if you want to do along with me, you can do it. Tomorrow I will share you this file. Then what we can do is we can directly. So how the data source generally looks like. I think we have only 10 minutes, so we will just quickly check how we can code it. So it starts with so we defined a port list, so it should have. These are very pretty much common in any of the C. And next, it should know this uh, same energy block, right? This is the feedback input, so it should know the status of the frame energy. Next, When the frame energy is ready and if the data source also receives a start trigger, what it has to do, the data source, what it has to do, it has to trigger start input of the frame energy, so that we can keep name it as start. Then it has to output the data samples, right? The data samples, and whenever it is streaming a data sample, it has frame energy module that the data request all the participants to just only see the screen, just concentrate here. You can do the programming later on. So how the template looks like for a FSM design. So first we have to do some or an ASMD. As ASMD or an FSM, more or less same coding. After that, register. I'm explaining once again. Those who have missed in the morning session, then can just concentrate. So this is a typical FSMD, ASMD, a kind of FSM based design. So I'm just highlighting the template. So after module and end module, after defining the port list, how the template should look like. Declare state registers and next state. You have to declare state registers and next. After that, what you have to do, sequential state next, what you have to do, you have to declare next we have an out. So sequential state register logic, as a word sequential, we are using behavioral model. So since it is sequential, and we are dealing with a synchronous reset, I want the reset to be active now. So the sequential logic, I need to define the conditions when reset and what it is supposed to do. So and next for the combinational logic, again always lock. And in this, since we are using a state register, sorry, FSM, it's a kind of since we are using we are doing update the state register, the combinational next state logic state underscore state reg should be it is the 0 to states, right? Wow. So how to declare a state? So local Here there will be more than two states, so maybe suppose I may use some states for the FSM. So those states are like S0, S1, S2 and S3. So each state is encoded with a binary code, so 2 bit of binary decimal. To hold this state value, encoding value, the state, and when it is reset, the FSM should ideal state, that is S0, and there is no reset. State next. On arrival of a clock edge, sequential logic will be updated with respect, and in the combinational logic, the default state next is, that means if you are not updating the combinational logic without doing, when you are not manipulating anything, the ideal value should be equal to the register value. Now, how to define the state switching conditions? So for that, I am using, and the case value should be the state reg. That is register what is the current state value of the FSM. If the current state is S0, then what are the, if the current state is S1, then if it is S2 state, if it is in the S3 state, then what? So this is a template. Next, in the output logic, what is we are supposed to do is, we have how many outputs? 3 outputs: start out, data sample, data value. For each output, you need to drive via a register. So for that, what we do, so this is the register, this is the next state logic, combinational next state logic that drives this register. So what I am doing is, so this register logic I will update, and then I will drive this register to this output. So for that, what I am doing is, by default, the start signal aim energy block should be 0. That's why I initialized to 0. Next, sequential state register logic ideally, and output logic we use data flow modeling as to this output. However, that output I am driving. Similarly, for the data sample, what I will do, another register, data sample register, we will read the value from the memory. See how uh, to follow. Finally, the output similarly for the data valid output, again we create a valid. Data valid, ideally it should be and in when logic and case if there is no manipulation. So this is how it looks like. Now the time is 5. I think I need to close this session over here. So I think overall template has been fixed properly. Only thing left is we need to define the state operations, that is S0, S1, S2, S3. In the state operations, we need to tell how our FSM is going to work. So basically the FSM needs to read the data from memory and output it. So that is the main functionality. So here one memory I have not added. So we will see tomorrow how to instantiate a memory within the module and then how to load data into that memory. And we will see how this FSM can be designed in these 4 different states to operate. So S0 is the ideal state. So how it will go to, how it will make state transitions, how it will read the data from memory, and how it will output the data. So after that, we will do a small simulation and we'll verify its functionality. After that, what we'll do, this data source will integrate with the frame energy module that we have designed today. And finally, we'll deploy it on FPGA and we will check it in its functionality in real time. I think I am done for today and we will catch up tomorrow. Mahesh sir, please take control. If you want to make any closing statements, you can make.
Nothing, sir. So, is there anything that I have to do now?
What, sir? Your voice is not audible.
Is there anything that I have to update to the students?
Tomorrow, once this is over, if time permits, I will show the interfacing of keypad and using the 7-segment display. Tomorrow afternoon session, we will dedicate it entirely for Ethernet packet generator hardware module. So for that, what you can do is you can take some tutorial session, maybe brief 15 minutes explanation. You can give the participants a brief idea of the Ethernet frame structure so that it will be helpful when we discuss the actual hardware models.
Okay, sir. Fine, sir. I will do it.
Okay, thank you, sir.
Thank you.